Hi, thanks for joining me today. I'm going to be going over problem 1 from week 2 of the Invariance Michaelmas term puzzle competition. As always, I'll leave a link in the description below with details to the competition. Anyway, this is the problem I'm going to be tackling today. We've got sort of a 100 by 1 row chessboard sort of thing, where we've got 100 squares, and each of those squares has a number on. And I labelled them A1, A2, A3, A4, all the way up to A99, and then A100 is our last square. And now each of these numbers here is in the set 1, 2, 3, all the way up to 100, and all of them are distinct. In other words, this set here is the same as this set here. So A1, A2, A3, all the way up to A100 is some permutation of 1, 2, 3, all the way up to 100. Now we have a character Yoshi who starts off on the square which is 1. So for example, if A4 was 1, then Yoshi would start off here. And then what Yoshi does is he moves to the square which has the number 2 on it. So that could be A37, for example. So he'll go from 4 then to A37. So A4 to A37, sorry. So 1 to 2. Then he'll find the one that has 3 on it. So say that's A2. He'll move here and so on. So he'll go for the square that has 1 on, square that has 2 on, square that has 3 on, all the way up to the square that has 100 on. Okay, now we want to know what is the expected value of the total distance travelled. So he starts off on the square that has a number 1 on, so if that was A4, he'd start here. Then, like as I said, if suppose the number 2 was A37, he'd then go to A37, so the distance travelled there would be 37 minus 4, which is 33. But then we want to know, well, what's the distance then going from the second square to the third square, plus the distance from the third square to the fourth square, and so on, and the expected value, of course. Okay, so if you want to have a go at tackling this problem, pause the video now and give it a go for yourself. And I'm going to get stuck into a solution. Okay, so let's get stuck into a solution. I'm going to let di be the distance travelled from I to I plus 1. So Yoshi starts off at square 1 and then moves to square 2. So that distance between 1 and 2 is going to be d1. Then he goes from 2 to 3, and that distance there will be d2, and so on. We want to work out the total distance, the expected value of the total distance travelled. Well, the total distance travelled is d1 plus d2 plus d3, all the way up to plus d99, because remember, he goes from 99 to 100 and then he stops. So the expected value that we want is the same thing as the expected value of d1 plus d2 plus ... all the way up to d99. But now we can use linearity of expectation to write this thing here as the expected value of d1 plus the expected value of d2 plus all the way up to the expected value of d99. Now, I'm not going to argue this too rigorously, but hopefully you can see that in fact each of these quantities here are the same, because there's no, it shouldn't be that the distance going from 2 to 3 is more than the distance going from 1 to 2 and vice versa. So in fact all of these quantities here are the same, so I can write this as 99 times the expected value of d1. So let me just quickly go over that line to that line. We've got 99 terms here, and I argue that they're all the same. Let's just look at these two here, for example. So this here corresponds to the expected value going from square 1 to square 2, the distance there, and this is the expected value the distance going from square 2 to square 3. Now, because each permutation is equally likely, the expected distance from 2 to 3 is going to certainly be the same as the expected distance from 1 to 2. I'm not really sure how I can sort of convince you more, but it's just sort of the symmetry and the fact that there's no reason for this to be bigger than that or vice versa. Anyway, from this line to this line is certainly true, so all we need to do now is work out what the expected value of d1 is, and then we're done. All we have to do then is just multiply through by 99, and we get the solution to our problem. Okay, so we've shown that the thing that we're trying to work out is equivalent to 99 times the expected value of d1. Of course, though, that means we still need to work out what the expected value of d1 is. Okay, let's just use the definition of expectation. This here is the sum over all possible values of x times the probability of d1 equals x. Okay, well, remember d1 is the distance between 1 and 2. But because we're only looking at the 100 sort of square chessboard, the distance can only be at most 99. The distance between 1 and 2 can be at most 99, and that's if 1 is at one end of the chessboard and 2 is at the other, or 1's at this end and 2's at this end. Okay, so we only need to consider the integers between 1 and 99. So this is a sum from x equals 1 to 99 of x times the probability of d1 equals x. Now, of course, we need to work out what the probability of d1 equals x is. Now, what I'm going to do is draw my 100 by 1 chessboard here. Maybe let's add a few more. Okay, not squares anymore, sort of rectangles, doesn't matter. Okay, so now I'm going to look at the case x equals 1, and then x equals 2, and then we can sort of derive a general formula for probability of d1 equals x. Okay, so let's look at x equals 1 first. Okay, now we're going to have to make, not assumptions, but to simplify our problem, let's assume that if we have ai equals 1 and aj equals 2, and we have that I is less than j. Okay, so of course one of these squares will correspond to 1, which I'm going to call ai, and another one will correspond to 2, which is j, and I'm going to assume that I is less than j. Now, of course, it could be that I is bigger than j, but I'm going to multiply my probability by 2 in the end to account for that, because there's a lot of symmetry here. The probability with I less than j is equal to the probability with I bigger than j, and then I can just double the probability here to work out the total probability. Anyway, x equals 1, and we have ai equals 1 and aj equals 2, and I is less than j. Well, what are the different ways we can obtain a valid sort of combination? We could have the 1 here and the 2 here. That's fine, because the 1 is sort of more left than the 2. And of course they're distance 1 apart. Okay, but of course we could have the 1 here and the 2 here. Or we could have the 1 here and the 2 here. And it can be in any of these sort of consecutive places, all the way up to the 1 here and the 2 here. Okay, so well, how many different ways are there of doing this? Well, there's 99. So probability of d1 equals 1 is going to be equal to 99 times, well, we've also got these squares here to choose from, and we don't really care what those numbers are, it doesn't matter. So there are 98 factorial different ways of choosing those. So 99 times 98 factorial. Okay, but remember, of course, we've got to divide by the total number of combinations, which is, of course, 100 factorial. Okay, so the probability of d1 equals 1 is going to be this thing here, but like I said, we've got to multiply through by 2 to account for the case when I is bigger than j. Okay, so that's the probability that d1 equals 1, so it's going to be this thing here, which I'm going to write here. And then we'll look at the case... Sorry, this is the case when x equals 1. Let's now look at the case x equals 2, and then we can derive a general formula for PD1 equals x. Then we can evaluate this sum and find our final solution. Okay, so we've just done the case x equals 1. Now let's look at x equals 2, and we're going to have a similar sort of approach. There'll be some ai, which has the number 1 on, some aj that has the number 2 on, and we're going to assume again that I is less than j, and then we'll multiply our probability through by 2 to account for the case where I is bigger than j. Okay, so the probability of d1 equals 2, well again, let's sort of count the number of valid combinations. We could have the 1 here, for example, and now the distance is 2, so the 2 wouldn't go there, it would go there. Okay, so that's a valid combination, but we could also have, instead of that, this one here, or similarly, this 1 here and then 2 in the next square there, and we can go all the way up to the final one here, which is 1, 2. Okay, well how many ways are there of doing this? Well, in fact, now that there are only 98, because we've got sort of 3 squares that is shifting along, and of course that will only occupy 98 squares. So this thing here is 98 times, remember the other squares, it doesn't matter what's in there, there are 98 factorial different ways of choosing those. Okay, but we've got to divide through by the total possible number of combinations, which is 100 factorial, and then multiply through by 2 to account for the case where I is bigger than j. Okay, so we get probability of d1 equals 2 is 98 times 98 factorial over 100 factorial times 2, and now notice that that's very similar to the case x equals 1, except here we had a 99, and here we've got a 98, and in fact we can generalise this. We get that the probability of d1 equals x, where x is some number between 1 and 99, is going to equal 100 minus x times 98 factorial all over 100 factorial and then times 2. It's not particularly clear, but yeah, just that thing there. Okay, so now let's shove this formula back into this thing here, and we'll be almost done in finding a solution. Okay, so we're almost done, and all that's basically left is a matter of algebra. We've just shown that the probability of d1 equals x is 2 times 100 minus x times 98 factorial over 100 factorial. Firstly, let's simplify this. The bottom is 100 factorial, which is the same as 100 times 99. Sorry, 100 times 99 times 98 factorial. So the 98 factorials on the top and bottom cancel. So this is the same as 2 times 100 minus x all over 100 times 99. But of course the 2 on the top, we can sort of divide the top and bottom by 2. So write this as 99 times 50 and get rid of that 2 there. Okay, great. Now remember, we want to know the expected value of d1, which is going to be the sum from x equals 1 to 99 of x times the probability of d1 equals x, which is this thing here. But we actually want to know 99 times of it, sorry. So 99 times the expected value of d1, that's going to be equal to 99, times the sum from x equals 1 to 99 of x, times this thing here, which is 100 minus x all over 50 times 99. Now 50 times 99 is a constant, so we can bring it out, and the 99 and that 99 cancel quite nicely. So this is 1 over 50 times the sum from x equals 1 to 99 of x times 100 minus x. Now, to evaluate this sum here, you could use a computer, for example, or you can use some standard formulae. The sum from x equals 1 to n of just x is x times x plus 1 over 2, and the sum from x equals 1 to 99 of x squared is a sixth times x plus 1 times 2x plus 1. I'm not going to prove those today. They're not too difficult to prove by induction, for example. But yes, you can evaluate this sum here by splitting it into 100 times the sum from x equals 1 to 99 of x minus the sum from x equals 1 to 99 of x squared, and then use those formulas that I just said. But you get that this sum here, and then of course dividing through by 50, the final answer is 3, 3, 3, 3, which is quite a nice number. And remember, what we were trying to work out is the expected distance that Yoshi travels. So it's 3,333. Anyway, that's the problem solved for today. I hope you have enjoyed this video. If you're new here, please do consider subscribing and checking out some of my other fun maths videos as well. But yeah, that's all for now, and I'll catch you in the next one. Have a great day.